This is a Learn recording for isotopic abundance, isotopes, and how common they are, and average atomic mass. The learning goal for this recording is I can explain what abundance is, and I can explain average atomic mass. I can determine which isotope's mass number the average atomic mass will be closest to. You do need access to the periodic table for these calculations or these questions. We can do these questions without math. I'm going to show you that in this video, but you still need access to a periodic table. You need to look up the atomic number for an element. You may need to look up the average atomic mass. You do need access to a periodic table. You can check online and access a periodic table very quickly by typing in P table into your web browser. And that will bring up a nice periodic table. P table, all one word. We also need an understanding, a very strong understanding of the atom and the three subatomic particles, as well as the regions of the atom, the nucleus, and the electron cloud. Remember, we need to know the mass, charge, and role of each of our three subatomic particles, the proton, electron, and neutron. That proton is the most important particle. The proton is the president. The president proton tells the atom what element it is. The proton is positive. The proton has a mass of 1 unit, and it resides in the nucleus. That electron is negatively charged. It does not reside in the nucleus. It resides or occupies the electron cloud outside of the nucleus. It's very tiny. It's extremely tiny. It has a mass of 0 for our purpose. The neutron resides in the nucleus along with the proton. It's neutral. The neutron is neutral. And it also has a mass of 1 unit. There are some additional points to know about the particles and the atom. I just wanted to give that review. A very, very, very quick review of the atomic number and mass number. The proton number equals the atomic number. When we go to our periodic table, we find 2 numbers there. The whole number is the atomic number. The whole number is the atomic number. The atomic number equals the number of protons. We also find a number with a decimal. This is not the mass number. This is called the average atomic mass. And we can change this to the mass number. The mass number is also a whole number or integer. We can round that and to the nearest whole number and get the mass number. This is a nice way to remember. Here we have ape. Atomic number equals protons equals electrons. In a neutral atom, the number of protons equals electrons. And here, man, mass number minus atomic number equals neutrons. So you can find the number of neutrons if you take the mass number and subtract the atomic number. The mass number is the atomic mass rounded to the nearest whole number. So that would be 19 minus 9 equals 10. The fluorine atom has 10 neutrons. We also have isotope notation. So if you see this type of notation, this in the lower left is the atomic number, and in the upper left, that is the mass number. So there are different ways to write information about an isotope. That's one way. Another way is in a sentence or in words, you will see a number after the name of the element. When you see that 14 means that's the mass number of the isotope. So you will often see it written like that. That means you're not going to go to the periodic table and find the average atomic mass and round it. You are going to use this for the mass number. If we just quickly, well, I'm going to move forward just so we can get to isotopes and average atomic mass, because that's the focus of our video. Okay, so here, let's think about isotopes and focus on isotopes. What are they? What's going on in an isotope? What is abundance? So let's take a moment to look at what we have on our screen. This is one isotope. Here is another isotope. So we have two isotopes to look at and compare. If we look at everything inside of these two isotopes and compare them, we can see what is similar and what is different. In the upper left, I have the definition of an isotope. Isotopes are atoms of different forms for the same element. So we do not have isotopes of different elements. They're always for the same element. But there is something different about isotopes. If we look at the first isotope, the name of the isotope is boron 10. And we can see that if we put it on a scale, the mass number is 10. So that's where the name boron 10 comes from. The second isotope, if we put on a scale, has a mass number of 11, and the name of the isotope is boron 11. If we compare the subparticles, the subatomic particles, what do we have? Well, we have 1, 2, 3, 4, 5 protons. And we have 1, 2, 3, 4, 5 protons. That makes sense because they're the same element, so they must have the same number of protons. If they had a different number of protons, they would not be the same element. If we look at electrons, 1, 2, 3, 4, 5 electrons. 1, 2, 3, 4, 5 electrons. So they have the same number of electrons. What about neutrons? We have one, two, three, four, 5 neutrons in our first isotope. And we have 1, 2, 3, 4, 5, 6 neutrons in our second isotope. So there is the difference between isotopes. So the difference in isotopes is the number of neutrons. And each neutron, if we remember, has a mass of 1 unit. And that's why there is a difference in the mass for each of these neutrons. So neutron number is the difference in isotopes. Each isotope has a different number of neutrons. Neutrons is the difference between each isotope of an element. Now, there is also something that factors into this in terms of how they affect the average atomic mass. We could ask ourselves, oh, that's cool. I wonder if there are a lot of boron 11 isotopes. Or I wonder if boron 10 isotopes are common. If I just went outside and grabbed 100 boron isotopes, what would I find? And here is what I would find. I would find that 20% are boron 10, but 80% are boron 11. So boron 11 is a lot more common than boron 10. And this is going to allow us to make some assumptions or predict something about the average atomic mass. If there are a lot of boron 11 isotopes, what do we think about the average atomic mass? Do you think the mass on the periodic table will be closer to 11 or closer to 10? Well, we're going to answer that question soon. Let's answer this question first so that we know for sure what an isotope is. This may be a quiz question. How are isotopes of the same element alike? They have the same number of protons. Does boron 10 and boron 11 have the same number of protons? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, that's true. They have the same number of neutrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Ooh, that's wrong. Nope, don't select that one. They do not have the same number of neutrons. That's how they're different. They have the same mass number. 10, 11. No, if they have a different number of neutrons, they have a different mass number. Don't select that one. They have the same atomic number. Remember, atomic number equals proton number. If they have the same proton number, they have the same atomic number. So we want to select that one too. Atomic number equals proton number. So we're going to select A and D for that question. That's how isotopes of the same element are alike. All right, let's go to our next slide. And our next question is, how are isotopes of the same element different? That's important to know also. Let's see what we have. It says A, they have different number of protons. 1, 2, 3, 4, 5 for boron 10. 1, 2, 3, 4, 5 for boron 11. They have the same number of protons. Of course they do. They're the same element. Don't select that one. B, they have different number of neutrons. 1, 2, 3, 4, 5 for boron 10. 1, 2, 3, 4, 5, 6 for boron 11. Of course they have different number of neutrons. That's the definition of an isotope. A different form because it's a different number of neutrons. They have different number of electrons. Now here's our rule. We're going to learn more about how this can change, but in a neutral atom, that means no charge. There's no charge for the atom. I don't know if I can fit this all up here. I might have, maybe I should have left that off, but I'm going to try to fit it. In a neutral atom, the number of protons, because protons have a positive charge, so you have to think about charge. Well, how can charges balance? What has a negative number, or excuse me, a negative charge? The number of positive protons, well, equals the number of negative charges, so that's the number of electrons. So in a neutral atom, the number of protons equals the number of negative electrons. So do they have a different number of electrons? No. We could have also just counted the number of electrons, but that's a rule we need to know.